I'm going to talk to you about a little bit about machine learning today, and we'll touch on what it is, what is the data that we use to feed machine learning, and how do we make decisions, what is the workflow that we apply in a business to help them realize the value from machine learning, and then a kind of thought about how it applies to you and your business. Machine learning is really predictive computing systems that become smarter with experience. Bill Gates' aspiration was to see computers that could see, hear, and understand us, and thought that it was worth 10 times as much as Microsoft. I'm privileged. I've worked with many of you in organizations across South Africa, financial services, retail, both big and small businesses, and some of the most agile startups in our landscape. But I'm also really fortunate that I work with an organization that uses data on a day-to-day basis to build every single one of our products, to gather customer feedback and enhance customer experience, and to build services that we deliver to you. As an example, on a recent visit to the Microsoft campus, I walked into a building, and there was a huge sign that said, "Warning, your every move is being monitored." And a good South African citizen, I was like, okay, campus security out to get the latest pickpocketers. But no, it was actually a machine learning exercise. They were using video cameras to record the movement of us as we were free-flowing pedestrian traffic moving through that building, so they could teach the Xbox Connect how to understand the movement of people in that context. When we think about machine learning and this resurgence in terms of conversation around predictive analytics, there's really 4 things that are driving that today. It's about the fact that we have more data. That data may be locked up in your data warehouse, living on top of Oracle or Microsoft platform, or the fact that it's locked up in data stores that are not traditional, documents and other places inside the organization. But there's more data, and more of this data is being born digital and available to us to base machine learning on. There's more computing power, and this computing power is coming from data centers like Google, Microsoft's Azure. All of those data centers that are there to provide scale-out capability are providing cheap, consumable compute power that you can pay for by the hour. There's also increased awareness from us as the consumer, but also from businesses, around customizing and tailoring the product offerings that we have to our specific requirements. That drives a requirement for you as a business to understand my requirements more specifically. But the 4th place is probably the most interesting for me. It's the one that takes all of these 3 previous ingredients and mixes them together. It is tools that are now based on those previous characteristics, the availability of large amounts of data, very cheap compute power, and combine them with a user experience that's accessible and consumable by the hour. Those are tools like Big ML and Microsoft's Azure Machine Learning. But machine learning isn't new. Let me bust that myth right up front. Machine learning has been around for a long time. The Machine Learning Journal celebrated its 25th anniversary some 4 years ago. So what we use from a science perspective in machine learning is the same stuff we've been using and refining over the last 25 plus years. I'm going to introduce you to a scenario that I'll use as an example. An organization, they sell bicycles. When you walk into their retail store or you interact with their website, they gather some profile information around you, some demographic information. They take those few pieces of demographic information around you, maybe your email address and phone number, they send it out to providers, and they build a comprehensive understanding of you from those providers around the demographics of you. And traditionally, this organization has sent you an email. Please buy a bike. Or maybe not. Maybe they've sent you a thing in the mail that says, here's a discount voucher on your next bike purchase. But this organization wants to change how it interacts with its consumers. It wants to make a more expensive buying motion for you. It wants to give people it thinks need a bike or want to buy a bike and have the capability of doing that, a bike. Ship them a bike, and let them ride that bike and send you the cash later. That's an expensive proposition, and it needs us to have data to help us understand that. So let's think a little bit about how we get data from information. Let's take a step back. What happens if I read you the sentence? After spending a day exploring the crowded streets of Johannesburg, Maggie discovered her wallet was missing. What are you going to think when you think about that story? Which of these words would you most closely associate with that story? What about these words? The story could have been that Maggie lost her wallet while she was arguing with some street hawker in downtown Joburg. Or you could have thought up the right story around her going up Carlton Centre and taking these magic vista photos of Johannesburg and its surrounds. But it likely wasn't. Let me add some additional information to that story. Let me tell you that Maggie is highly intelligent. And like most other highly intelligent women, she's chosen a partner that is significantly less intelligent than she is. How many of you associated with that with a statistical problem? With the fact that that information is purely based on a regression to the mean. The fact that if she is an outlier, she's highly intelligent, means that she's most likely to have a less intelligent partner. We don't. We tell ourselves stories when we're presented with information. These stories are filled with bias. How many of you chose pickpocket? Hands? How many chose pickpocket? How many chose angry? Okay. It's a significant story, and it shows the biases that we have. We also have a very low level of intuitive understanding of statistics. The information that's presented to those people, the salespeople in that company, when they want to decide whether to give a person a bike or not, the demographics and the understanding of those demographics is not immediately obvious to that person. When I think of machine learning, I immediately jump to Arthur C. Clarke's quote, that any sufficiently advanced technology is indistinguishable from magic. I think machine learning is magic, and I think if you think about how machine learning is applied to your life and how it can change the things that you do, that is the value you're going to get out of it, and that is going to be my challenge for you today. But if we're not using data to make decisions, we are doing little more than guessing. Let's think of the biggest machine learning problem that there probably was by volume. The US Postal Service delivers 150 billion pieces of mail in a year. That's a little bit different to the South African Postal Service. But in 1997, only 10% of those messages, those mails, were understood and routed by machine. Why? Because this stuff is hard. Understanding that handwriting and what it represents is something that we as humans, I think most of you can read every single version of that, find easy, but for machines is really hard. If there's any C++ programmers or C# programmers in the audience, and I gave you the challenge of writing a program to go and solve that, I think most of you would leave the room. It's really hard to do that programmatically. But what we can do is provide feedback. We can show the machines what that means, and from that information and the algorithms that lie underneath that, they can derive an understanding of what that information is. And through that, today, 98% of mail in the US is routed by machine, through that machine learning process. So let's think a little bit about how this works. So we get these handwritten samples, and we have them by the millions, by the billions, by the hundreds of billions in the case of the US Postal Service, of letters handwritten. And what we do is we capture the information that we as humans can understand associated with that. We create training labels against those training examples that we've got. And we apply machine learning to decipher the characteristics associated with those labels that we've applied to the training examples. And we create what is called a classifier. In this case, an accurate single-digit classifier. It'll take a handwritten character, and it'll understand it as a 2 based on the information. We've used some programming to create the process, but we've taught it with the data as it's arrived. And through that, we've been able to deliver a system, in this case, that sorts mail. But there are other great examples. Microsoft's worked with Carnegie Mellon University to help them optimize their power usage for their heating. And they've done that through integration with sensors that provide temperature, humidity, movement, and scheduling information to a machine learning algorithm. The interesting thing with this type of integration is those sensors are usually around in buildings today. Think of this building. It's got sensors in here to control the air conditioning, humidity, temperature is going to be there. There's definitely burglar alarms in this building to tell us where there's people, and there's video cameras providing that information. All we needed to do was tap into those sources of information and provide a machine learning algorithm that could work out when it was an appropriate time to turn on the heating so that the room that the people who they knew were going to attend, because that was in the scheduling, would arrive in that room and the room would be at the right temperature. It depended on the number of people and those external factors that were already available. And we've implemented this with Carnegie Mellon in this environment. But here we can think about the cliche examples, and there's lots of them. Churn analysis, recommendation engines, forecasting, fraud detection. But again, let me say, if and how much your machine learning changes your life is going to depend on how you apply it. Think about how you can use it in the scenarios where you would like to be able to predict the future, or you would like your machines to be able to understand something that they can't understand today. So let's go into the technicalities of what's here. There's 4 types of common classes of machine learning problems. Classification, dividing groups into multiple classifications. Regression, fitting a line onto some data. Recommenders, you've probably all run into those. And anomaly detection, where we want to pick up the outlier associated with some data. Really, the process of doing this is to create, in these 2 examples I've got here, a line that accurately separates those 2 groups of points. So if I added some more green points on the side up, the left-hand side of the thing, the line would become more upright. If I added some points on the right-hand side of the graph, on the right, the line would again become more upright. And it would predict the next point that came along, or it would be able to classify, in the case of the one on the left, which group of things that point actually belonged to. So we use the historic data to teach us about the future data. If I want to implement this, I really need 2 things. I need a decision, a well-understood business decision, and the data to support it. The data about the characteristics that I use to make the decision, and the outcomes. And I now have an historic set that I can use for training. I would then follow this machine learning data flow, and it applies to all tools, not just to the Microsoft set of tools. This workflow says, define the problem and understand how you get that data. You want it in its native form. You flatten the schema of that data, so you have one row representing the features that are going to help you with that outcome, and the outcome itself. And that becomes your training and validation data set. You can do things like adjust the scale of some of the data points so that it better feeds the model. You can choose specific sets of features. But then you train a model. You pick a model and you train it. And you can, in some cases, have complicated models where you might need to get actuarial sciences to help you understand the parameters. But in most cases, you can just choose a variety of parameters to test. This is a data science process. So when we've run it, we validate it, and we understand the outcome, and we go back and we modify the process. It is an iterative process. It gets repeated over and over again. So here I'm going to run you through, using the Microsoft tools, how we would do this. You can drag on a data set into the surface that is our tool. And it'll allow you to have a quick view of the analysis of the data. There are different columns in this data containing things like the number of children, the age of the person, their credit history. But most importantly, it shows whether they bought a bike based on our ordering and invoicing history, whether they bought a bike. We will then split that data into two sets. One, to train our model, and the other one, most importantly, to validate the outcome, that this model is giving us what we want. And then we connect it up with the model itself. In this case, I've taken a two-class logistic regression as the example, because maybe it sounded nice, and there's very little parameters I need to tune on that model. I select that I want to get the bike buyer as the outcome from the data, and I feed it with that data set that I've now split in half. I keep half of it, or more than half of it, to validate the model. And that bit of data that I've kept to validate the model, I then score against the result. So I use the model, train it with one set of data, feed it with another set of data that it'll predict the outcome, and I compare it with what happened before. And that way, I can get an understanding of how well this model is working. I haven't made a decision dependent on it, but I can get an understanding of how well it's working. In this case, we've got 129 false negatives and 108 false positives. That's 129 people I wouldn't have sent a bike to that might have bought a bike, and 108 people that I wouldn't have sent a bike to. So what I can do is then choose a different model, choose a different way of analyzing this data. And here, I've chosen a boosted decision tree as the way to do the analysis. And I'm going to compare the results of those two things. With the improved results, what we can do is we can now see that there are significantly less false positives and false negatives, to the point that if I'm going to get 546 sales out of sending people bikes, I might be prepared to accept the 56 that might come back to me and provide me with the overhead of having to repair and service that bike before I can send it out to the next person. The machine learning process is only useful to you if you put it into your business. So the call to action for those of you who have a look at machine learning is to put it into a place where you can use it. It's an experiment in the data center when we're doing that modeling. It becomes an experiment in your business when you start using it in your business. And it's really, really easy with some of these tools that take advantage of the internet capabilities through things like Azure Machine Learning or Big ML, where we've got a way to get in at a very, very low price point and experiment and see what that looks like. Then monitor what it gives you in your business and let that drive the outcome of your business going forward. I hope I've been able to show you that machine learning is really easy to implement. If you like my examples, have a look at Thinking Fast and Slow by Daniel Kahneman. It explores the falsehoods that we have in how we think about data sometimes as humans. Thank you very much.